So, hello again. Tonight we're going to talk about, well, it's kind of a clickbait title again, Index of Reality. There are physical properties that we've laid out as earmarks for what we think of as boundary conditions or limits. Um, they have caveats associated with them because the numbers won't be what the numbers are expected to be unless it's under the following conditions. So what I've done is chosen a different aspect of physics and reality and said, what if that was the basis of our index as opposed to what we have? Because we have what we have today. So there are quantities baked into the structure of the universe. We recognize them as measurable transitions and limits. They're certainly recognizable as what we might think of as constants, but they aren't really. So we use them in our systems of measurement. But if you dig below the surface a little bit, you'll find out the caveats of, yes, it's a constant, but only if, and under this circumstance, and then it's kind of close to that, but it's not exactly that. So we'll get into a little bit of that and then see if we can't find something else that's a little better. So the two favorites are when water freezes and when water boils. So the transition temperature of liquid water to ice and then transition temperature of liquid water to a vapor. And most people think of those as 0 degrees Celsius and 100 degrees Celsius, or 32 Fahrenheit and 212 Fahrenheit. In reality, the boiling actually takes place just a fraction of a bit less than that, 99.97 and 211.9. By the time you get to 100 or 212, it's already there. So as we've been able to improve our systems of measurement, we found out that, well, 100 isn't precisely 100, it's 99.97. And as we have better technology, it'll probably be 99.96892 something or other. As we get finer and finer resolution, we'll examine the actual molecular structure of things as they transition based upon their energy readings, not just based upon, like, when do the bubbles start showing up in the water? But even these, they only are what they are under certain conditions. Like, well, the water needs to be pure or fresh, because if you add chemicals to the water, it's not perfectly pure. You won't get precisely, 99.97. You'll get a number higher or lower than that. And the atmospheric pressure. The atmospheric pressure has to be 1 atmosphere at sea level. Who's sea level? Because there are places like Lake Titicaca in South America where the level of the water is much higher than it is at the Atlantic or Pacific. And the Atlantic and Pacific aren't actually at the same height. So it's an average. And it's not like a precise number. Most people will toss it around and say that's 1,000 millibars or 1 bar. Well, it turns out it's a little more finer in resolution, that it's 1013.2 millibar. So these things that we think of as precise numbers in nature have conditions. So what would be the atmospheric pressure on Mars, Venus, the Moon, or Enceladus? Because that atmospheric pressure is different. So the point at which water would freeze or boil on those places would be different. And also because we're counting in base 10, if you have an alien who has no opposable thumbs, just has 4 and 4, they're not going to use base 10 for counting these things. They're going to use base 8. So the numbering systems are different. But I found this interesting. There's a STEM class where they teach kids the fact that water boils and freezes at slightly different numbers based upon the things you add to the water. So if you want water to boil higher, you put in a little glycol. We think of that as antifreeze, which is actually meant to raise the boiling temperature as well as change the freezing temperature. Water will freeze at a higher point if you add a little sugar to it. Water will freeze at a lower point if you add a little salt to it. So, between pressure changes and a little bit of chemistry, those trusty boundaries of Celsius of 0 and 100 are a little sloppy. So depending upon the circumstances or the caveats, what we think of as constants don't behave like constants. They behave like known transition points that can be varied based upon circumstances. Let's pick another one that we think has always got the same value. The speed of light, it's a constant, right? Well, kind of. If it's a vacuum, well, what is a vacuum? Well, it's zero air pressure. Well, actually, what you're trying to do is to get no molecules to get in the way of the light moving through whatever the container is. And so we call that a vacuum. But there's different degrees of vacuum. There is, standard vacuum, which may be, 29 or so inches. And then you get further than that, closer to 30, and you get a drawed down commercial vacuum. And then there's the vacuum of space around the Earth. And then there's the vacuum in voids in the universe. That would probably be as close to vacuum as we're going to get. And we find out that, if you don't have a vacuum, if you have materials that the air is moving through, even transparent materials like helium, the gas, it's going to move at a different speed through helium than it does through a vacuum. And all sorts of things, to the point where we created this thing called a refractive index. And that's light moves at the speed of light, except through this material. You have to factor in this number that in a vacuum, a good vacuum, it's 1.0. So in something that's a little denser, has a little more molecules in it than vacuum, that number is going to be greater than 1.0. And for diamond, it actually gets up to almost 2.5. And then you find out that, that whole speed of light thing, it's not actually the speed of a photon moving, it's the speed of the wave phase change. So it's a propagation speed. It's not a particle movement speed, which means you can actually have a greater than zero, a zero, or a negative refractive index. And they've also found out that a vacuum is not truly an empty void. They found out that a vacuum contains fields, and that these fields may actually be the basis that constrains light as a bias of 1.0. Absent these fields, maybe the 1.0 is less, and the speed of light in a void is faster than the speed of light in a vacuum. So this thing that we think of as a constant and upper speed limit, not quite so grounded as we think. And now we've got metamaterials. We've actually created what are known as left-handed negative index metamaterials. This is where that index of refraction actually goes negative. And if it goes negative, what would be the speed of light in a negative material? We're not going to get into that, because as you cross from a number less than 1.0, closing on a number that's 0, you get to divide by 0, and therefore the speed of light becomes mathematically implausible. Divide by 0, infinite. So we'll leave that for particle physics to figure out. Suffice it to say that the speed of light varies based upon the material that the light is transferring through. So much for it being a constant. So I said, is there anything in nature that I can call upon to be a constant of nature that wouldn't vary based upon atmospheric pressure or the material it was associated with? And I said, if we wanted to do that, we really need to change what we think of as 1. We need to change the basis of 1. And why is that? Well, because we already know that speed of light in a vacuum has an index of refraction of 1.0, precisely 1.0. Well, if we're going to use a different physical property to be our unitary count, then that changes what one means. So this would be a bit tough, but in other disciplines, we've done that. But just think of one as falling into number theory as being a singular item. How many pencils do I have? I have 1.0 pencils in my hand. Well, when you go to measure materials, that 1.0 may be something that's ratio based and not based upon counting theory. So here's where the not quite $3 word comes into play, something called metrology, not to be confused with meteorology, which is weather. This is just the science whereby we count stuff. We count stuff, we measure stuff, we evaluate stuff. Is it this value or that value? So the metrology of 1.0, if we change that, we might have a better constant. Now, why use a constant that's a ratio versus an actual measurement? It's because measurements are based upon a base, and that base changes based upon your units of measure. So you can think of it as, I want to measure the weight of something on Earth. I can measure it in ounces or pounds or grams or kilograms. So if I choose a unit of measure and not a ratio, I've always got to muck around with translating units from one system to another. But in other aspects of science, there's a unit called radians. Radians are a ratio between the diameter or radius and the circumference of something. So rather than measuring stuff in angular degrees, where we pick an arbitrary 360 degrees, I'm measuring from 0 to 2 pi with no units at all. So the angle sweeps all the way around the circle, that's 2 pi. If it sweeps halfway around the circle, that's 1 pi. So we have no unit to go with that. It's just a fraction of 2 pi. So that's what we really like, is to come up with a ratio, not a unit that requires a unit of measure in order to know what we're actually evaluating. So there's this group called the SI, French, turn it around the other way, the Institute for Standards, the SI units. And they have this lovely wheel that shows you the units we think of on the outside, like kilograms and meters and seconds and amperes and degree and units Kelvin and moles. But on the inside, it's the underlying fundamental constants that you're supposed to base this stuff on. And this is how we change from one to the other. We'll see that, for example, what is the duration of a second? Well, a second is the number of oscillations of a cesium atom over a period of time when we count those. Well, how do we know what to count to? Well, we started from a second and then we took the reciprocal and worked backwards. So we defined what something is based upon what we want it to be, which is kind of like you got your answer before you even answered the question. Mass, we have the kilogram. Oddly enough, this is the only one of the scaled units. Why couldn't we measure it in just grams? Because amount of a substance is moles, electric current is amperes, luminous intensity is candela, but candela has a human physiological response based upon human eyes. The time, what's the duration of 1 second? Well, 1 second is how many clicks we get from an atom, but that's length in 1 second, so that's meters. So they're feeding upon one another. But each of these is based upon an underlying arbitrary constant, and all the outer values are derivatives of those. So if we go back and we look, we'll find here's our defining constants. So the underlying constants, that this is where it gets to be like, ignore the man behind the curtain. Cesium will click at a defined rate. And if you allow it to click 912631770 times, that is 1 second. But that's an arbitrary number of clicks in order to get to what we've chosen to be 1 second. In other words, it ends in 770, not 769 and not 771. It's 770, and that's 1 second. But okay, so if that's 1 second, and you measure the speed of light in meters per second, then you're saying things per second, because the transition frequency is the number of things per second. So you now have the speed of light based in an arbitrary number that is defined by the same arbitrary number. So if I say, how long is a meter? I'm saying a meter is the speed of light in a vacuum for a certain distance. Well, how long is that distance? Well, it's the number of things that occur in 1 second. But it's measuring meters per second in a number that's defining seconds. So you'll see a lot of this where kind of ignore the man behind the curtain, don't ask too deep a question. The Planck constant is measured in joule seconds. What is a joule second? Well, a joule is 1 watt second. So 1 watt second seconds? It's circular. Ignore the man behind the curtain. Elementary charge is measured in coulombs. Well, you've already got a unit of amperes. Well, you're measuring an ampere in coulombs. Well, what's a coulomb? A coulomb is 1 ampere. What? So you've got coulombs that are the basis for amperes, but amperes are coulombs. But what you could do is dig beneath that and say, well, it's actually the discharge of a certain quantity of electrons. Okay, well, what's a discharge of electrons? Well, that's voltage. Okay, so you're defining voltage by 1 joule per coulomb. Why don't you just count the damn electrons? You did that with the hyperfine cesium. You have an arbitrary number of them. Why not do the same thing as an arbitrary number of electrons is an ampere? Well, there's the number. So they could have just said, much like it's an arbitrary number of clicks of cesium, elementary charge is the transfer of a counted number of electrons. I don't know why they don't do these things. The next one is temperature. Let's measure temperature by the movement of molecules, by the energy in a system that things are moving. As we reduce the energy, we get to less and less movement. Eventually, we are going to come to a point where things pretty much grind to a halt, and we have this thing called the Boltzmann constant. And how do we measure that? Well, we measure that in Kelvin. And what is a Kelvin? A Kelvin is joules, or energy, per Kelvin. Did we just measure Kelvin in Kelvin? Ignore the man behind the curtain. The one that's pretty good is measuring the amount of substance or moles of it. We have a constant, the Avogadro, and it's a particular arbitrary agreed upon number, and that tells us how much of a substance we have. But luckily, it doesn't require any further decomposition or units. It's just a number. Good. Finally, they have a good one. And then they flip the other way around. They said, luminous efficacy. Well, that's how they get to their candela. But the luminous efficacy is based upon 540 terahertz wavelength, or sorry, frequency. And when you see what that's based upon, it's 683 lumens per watt. Well, what's a lumen? A lumen is a discharge of energy at a particular wavelength that is biased by human retina perception. Okay, so if I was somebody from somewhere else who had a different retinal structure, then one candela would be a different number because it wouldn't be centered around 540 terahertz. So what you think of as a constant has all these caveats associated with them. And if you remember back to grammar and defining things, there's this old adage that says, never define something using itself. And if you're going to define a value or a definition, don't use itself to define itself because that's just circular. Well, some of these things are occurrences per second, but how long is a second? A second is an arbitrary number of occurrences per second. Okay. And then you've got, as I said, Kelvin defined as Kelvin, based upon joules as energy in kelvins. Okay.
Monroe, I have a question for you.
Yes.
Because you keep, well, I don't know. It seems to me that you have mentioned a couple times, like their retina may not be the same as ours, so they would not see things the same way.
Yes.
And that seems to me to be indicating that there may be an alien race that didn't see it that way. And my question is that based on that, that's what I've heard. Yes. Hopefully I heard it correctly, that we don't look at, I mean, I wouldn't look at or expect these people to be looking at that they have to give definitions for an alien race that we don't know exists at this point in time. I would think we just want to make sure that everybody in our planet, that we all communicate. So, and I gather scientists have a better grasp on communicating to each other than we do with language somewhat. I mean, because they use these definitions type things to communicate, to try to be more specific when they're communicating. I don't see I mean, once we do locate an alien and they do have a problem with hearing or seeing and our kind of thing, then I would think it would be the same thing we would do with language. Once we learn there's some other language, we need to develop another word, or something. And then we would start to have a dictionary based on people from this planet versus people from that planet who have problems with their eyes or their ears. One of them has problems, so that we would just, because you never know, know what you don't know. Anyway,
what I do know is there are certain women on this planet that do have a different spectral response than the rest of the people on the planet. So you don't have to go for spooky alien extraterrestrials before you get to the point where not everybody on this planet has retinas that are centered on 540 terahertz.
So they should have like a note to it. Like
so 1/4 of the women on the planet are tetrachromat.
Yeah. So,
but I mean, maybe they could put an asterisk at it that this does not include those people. Is that what you would be saying?
No, that would include it. All those measurements are arbitrary.
Yes,
but
that's the point.
They are arbitrary because they were used based on something that was physical before. Let's say candela. Candela, in translation, it means candle. I mean the light of a candle in a specific distance, and that was given a number. But that was something that was not established to be the same number, precise number. So arbitrarily, they showed specific physics that could keep that same number constant, and that would be the base of the count of the efficiency of the light. Just in the case of the meter, or it was the foot of some king, or it was the second was, dividing the time that the sun goes around the planet in the equator. That's all arbitrarily because of tradition. And then after tradition, the SI constants were defined to keep them constant, and we didn't need physical objects to calculate them. We use calculations in physics, so we would not need a physical pattern to actually split out all over the world. That would not be necessary. The gram kilogram that loses atoms while they polish, and you would have errors in count. So they use the physics using pure numbers to actually establish that pattern. Now, the establishment of that pattern is totally arbitrary. It's what the tradition came about.
So
So you're not complaining about these things being the way they
no, no,
are.
no.
Yeah.
I'm just saying that most people don't realize how arbitrary these things are. They're just taken as, well, these sciencey guys came up with them and they're constants, right?
Well,
They're
I
just
think you're right. I
arbitrary
think that
numbers that
we
were
tend to
selected.
think, tend to think we think that scientists and they get pinged a lot because if there's something changes from the number that they had, we come back and say, well, you told us it was such and such number, and we figured that that number was the word, the number.
Yes.
And then when they come back and say, oh, well, we found out this, we say, see, science isn't right.
Well,
But here they have
100 years ago, that would have actually been the case because a lot of these very fine counts or decimal digits are as of the last 50 to 100 years because our technology's improved to make the measurements. So, the cesium hyperfine transition frequency is something that's new in our lifetime. But, what the number was before then was based upon an ever increasingly accurate value. This is just today's accurate value. We may come up with a new technology that allows us to measure things more repeatedly, precisely, and these numbers might change a little bit because science does that. As the technology improves, we get more precise, higher reliability. But the one that we encounter on a regular basis is when you go to Home Depot or Lowe's and you go to buy a light bulb and you want one of a certain brightness, you buy it by watts. Oh, but that doesn't work anymore because now they're LEDs and they consume a lot less power than they used to. So you don't go buy a 60-watt bulb because that 60 watts can now be generated equivalent amount of light in 8 watts or 6 watts. So you go up, buy it by how bright is it? Well, the brightness is measured in ANSI lumens. Okay, different people will perceive that same light bulb as being brighter or dimmer based upon their own retina. So that's where it strikes home is they're using what they claim to be a constant, a unit of measure called an ANSI lumen, and it turns out it's kind of in the ballpark, but you can't count on it as being a constant because there's human physiology involved in the measurement. Now, they could come back and say, well, we're going to measure it as photons of a certain wavelength quantity per second and call it flux. But now you're changing your unit of measure that people have come accustomed to of lumens. And what the hell is a flux? Is that like that flux capacitor thing from Back to the Future? No, it's the quantity of photons per square millimeter per second. How do I evaluate that? I can't. So we arbitrarily not only pick the basis for these things, we arbitrarily keep to them even when the technology that's generating the thing that we're measuring changes dramatically. It went from a 60-watt bulb that's just as bright if it's an 8-watt bulb. Oh, it's 820 lumens. What? Kelvin value? Because, a bright blue-white light appears brighter, but it still uses less energy because of the chemistry generating the light. So these things are going to change over time. And the goal of the SI is we'd like to find an underlying natural ratio, reality. We want something where we don't have to have all these caveats. And we'd like to not have to define things based upon the same things that we're defining. So we'd rather they weren't circular. So what do? We've got to keep looking for other things in nature. So we would like to find a unitless unit, something that's a ratio. Well, if you look underneath all of the technology used to measure all of these things, they're electronics in nature. So what they're doing is they're counting electrons. They're clicking off counts of things that were detected. Well, how do they know how many they can count? Well, it's based upon the chemistry, the atomic structure of the sensor material. You know, what kind of material you're using to collect your electron to photon transitions. Well, that gets you your count, your photoelectric effect. You're taking in photons, and then you're creating electrons, and then you're counting the number of electrons to get you to a digital value of voltage or amperage. So all these counts are based upon either electrons or photons. So you can take all those other numbers that they've got and get to their underlying root counts of either photons or electrons. Now, the scientific community could do that, and you would now have, based in nature, a singular count that requires no unit except the integer number of those things. So why doesn't SI count everything as an arbitrary wavelength or frequency of photons? Because they've done that elsewhere. You know, Candela's got a bias of lumens. They could come in and say, well, much like we chose cesium as our atom of choice because it's easy to work with, we could choose something else and say, we're going to count up the number of electrons based upon the number of photons that we're gathering in a certain sample period, and that becomes the basis for these units. But they'd have to pick some arbitrary wavelength of photons and some arbitrary chemistry of their sensor, and apparently they're just unwilling to make that next leap forward. So they'd like to have something that's unitless. They'd like to have something that's a countable quantity or that is based upon a ratio like radians, but it's just not clicking with them. And then we get to the other human physiological biases, obviously counting by tens, the human eye central wavelength bias, and then we get to 24 hours in a day, and then we count things by days. Well, if you understand the Earth's rotation, you'll know that it's not precisely 24 hours, a little less than 24 hours, and that the rotational speed varies plus and minus by a small amount. So even 24 hours in a day is not a constant. Well, how far, how about how far light travels in a year, a light year? Well, that's based upon an Earth year being 365 days, but we know because we have a leap year that it's not exactly 365. Every 4 years, we got to throw in another day because it's neither a constant nor is it precise. So we have additional caveats to even the basic stuff we work with, like 24 hours in a day and 365 days in a year. So we could make these things more precise, but we got what we got, and it's easy, so we're not going to mess with people's heads because they're still reeling from back when we tried to go metric for everyone. And, 24-hour clock might be more precise because you don't have to worry about the whole AM, PM thing, but I doubt there's going to be any worldwide societal tolerance for that one. So transitioning these things to more integer countable and focused on the physics of the event rather than some arbitrary value wouldn't be socially acceptable by the public. And for the general public, let's keep it simple. They don't have to worry about this thing on a day-to-day basis. But for those people involved in certain aspects of science and technology, getting the distinction right between inches and meters is important. Otherwise, you can crash into the moon or Mars, which they've done recently. Well, not recently. Recently, the moon, but not too long ago, Mars. So what about the numerical bases themselves? Computer folks are used to dealing with different base numbering systems, binary, octal, decimal, hexadecimal. And they also realize that even the numbers that we know of as base 10, they're actually stored in the computer in base 2. If you've written any programs in BASIC or other you'll realize that in BASIC, things start counting from 1. In most other programming language, things start counting from 0. If you're into cartography or measuring stuff on the sphere of the Earth and such, coordinates are based in sexagesimal or base 60. That's very Earth-centric and arbitrary. Radians, opticians are more versed in that, so radians is a bit better. Physicists are acquainted with Kelvin. That's a little bit better. So people that work in science and math are used to being involved in numerical bases that change and the conversions for them. But the general public typically is in a simpler basis than that. So as I said, science and technology is used to different dealing with these things. And there's even units of measure that we've given up on. And who deals with those anymore? People might have heard the word furlongs, measuring distance in furlongs, like horse racing. Pennyweights. This was when a penny was a certain weight. You could measure things by pennyweight. Buckets and bushels, rods, but those have fallen out of favor. So long as whatever new metrology they come up with is unitless, internationally established, and conversion algorithms are available, some community, science and technology, will be able to cope with it, not a problem. It's the general public that rejected the meter. It will probably be the Luddites with the monkey wrenches or wooden shoes that they called sabotage. But it's, in the case of metric, it was businesses that just didn't want to spend the money to change their documentation and process, the money delta. For the public, it's just about adapting to things. In the US, one of the last nations still not using the metric system, we think of it as having to adapt. But for the other billions of people on the planet, when they encounter the US system of measurement, they're the ones that have to adapt. So we're not in the majority, except when it comes to money and technology, and then we are dominant. So, but once we improve the science where everybody can use it, everything improves. Okay, so I feel like I'm back in my product marketing days where you bury the announcement lead so as to avoid the knee-jerk response from your audience to paradigm shifts. So we're looking for a unitless measure, so we don't have to be converting things back and forth. And we're looking for one that doesn't have a lot of variability in physics. Like we don't have to worry about temperature and pressure and salinity and just stuff that muck stuff up. And we'd like to count a known number. Well, there is this thing called the fine structure constant. And as of our current position in the timeline of the universe, it is a constant. It's also known as the Sommerfeld constant, or the unit of measure known as alpha. And it's very much known in science. It is the strength of electromagnetic interaction between elementary charged particles. And it's unitless, as in it's basically the attraction of materials at the subatomic level. And we see it in spectra in the universe. So it's consistent across the known universe as this value. And it's a ratio, but not precisely. So if you want to grossly approximate it, you can just take 1 and divide it by 137. You'll come up with this number. That's a gross approximation of alpha, the fine structure constant. The way you actually calculate it is with a ratio of constants. So it's natural log E squared divided by 2 elementary not zero Planck constant times the speed of light. And that will give you the exact value of the fine structure constant. So it can always be known to be this value. And unlike pi, it's not a simple ratio of like circumference to diameter. It's actually fields. And the fields themselves are constant, so their interaction energy level is constant. And we've measured this value to a very precise, high accuracy, 7.2 297,352,5693 times 10 to the minus third. Notice there's no units there because it's the interaction between two particles, so it's just a value. So if we wanted to measure other things in the universe, why don't we base them upon the FSC? Think of it as, if you remember the old style barometers or the analog scales you would stand on to measure your weight, there was always an adjustment for where zero is. So if you took a measurement of something related to the FSC and you came away with this number, then anything that's based upon a 0 or a 1, you could adjust by the FSC and get a much more precise value for it without having to, circular things of it's this many things per second or this much divided by 1 second, and it chases itself. So if we used alpha as the new basis for calculating 1.0, how would that work? Well, the first thing you're going to hear is, lots of people making noise and stomping in the corner of the room going, they're doing it to me again. They did it with metric and then trying to get me to the 24-hour system. And now there's this alpha thing that has lots of digits in it. Well, if everything can be converted, then you don't have to worry about that because you don't worry about metric. If you measure stuff in feet and inches, you still do. So underlying values could be measured in the fine structure constant, and we wouldn't have to worry about the temperatures and the pressures and just measure them based upon FSC. Kind of like why we chose cesium as the source for our timing fountains to count off clicks. We could use the fine structure constant the same way. And if you're thinking about, well, it would be a small fraction of things and it'd be these weird decimal like number things. Remember, the Planck constant is a value times 10 to the minus 34th. This is only to the minus third. So is it sufficiently fine-grained? Yeah, because it's got lots of decimal digits. So we know that water boiling and freezing and the speed of light, these are stipulated conditions and that they vary on other space environments and on planets. The fine structure constant would be harder because we see that in space. But even the fine structure constant has its caveats. Based upon the time scale of the universe, the FSC may have changed a little bit. We know how to express it. We know what its value is today. But in the early universe, when physical phenomena were a little different, the fine structure constant was probably different. And in the future, as we finally catch up with whatever dark matter and dark energy are, and we talk about trillions or more years from now, the end of the universe, we may be talking about a fine structure constant that might be different. But right now we're in the sweet spot when it's going to be a constant for a long time, and we can algorithmically define this as this ratio, mathematically expressible. So maybe we judge the fine structure constant as a gauge of the age of the universe and say, here's what it is right now, and we don't have to worry about it being different for 10 billion years. And that's fine, because that's much better than saying, well, your pressure has to be just right and your temperature has to be just right and the salinity's got to be this and there's got to be no particles in the vacuum. This would be a lot simpler. So you finally got your constant. It's a constant based upon a ratio. There's no stipulated units for it. It is arbitrary, but I think it's a better place to be. So I like to think of it as it's a right-sized square peg for a right-sized square hole. Somebody noteworthy in physics, Richard Feynman, said he understood the fine structure constant very well. And he said that if the fine structure constant were a different value, the universe might not hold together. It might not even exist. So his comment was, it's one of the greatest damn mysteries of physics, a magic number that comes to us with no understanding. It is what it is. And if you've ever heard people talk about why isn't there an equal amount of antimatter or why aren't we living in an antimatter universe, it's just where things fell out and we got what we got. But what that points out is if there are other universes where a different value for the fine structure constant is possible, those would be different universes kind of pegged as having different size square holes. But ours is what ours is, and until we find others that use a different number, we have our one constant that we can count on that's a ratio that has no units, and we can base everything based upon that. It is currently what we got. If we suddenly came to our senses and said, we're going to use this strange value. Historically, there's a guy named Wolfgang Pauli, who's a noteworthy particle physicist from days gone past, who said, when I die, my first question to the devil will be, what is the meaning of the fine structure constant? So even noteworthy personalities from particle physics knew of this value, knew what it described, but not why it was the number it was. Maybe it's just it is what it is. Maybe it's kind of like, we got 10 fingers, let's count things in tens. Even though our computers count things in base 2, we still find a way to get to 10 because that's what we got. And when we look out into the universe, the FSC appears to work the same way elsewhere. And where we discovered this elsewhere was photons have a characteristic known as a spin. And if the spin's going one way, you get a spectral line at a certain wavelength. If the spin's going another way, you get another line, and the separation between the two is the fine structure constant. So our current science is based upon counting from 1.0, but if we align the 1.0 with the fine structure constant, maybe ET would be more willing to speak with us because now we showed both intellectual reasoning and scientific progress. How would that affect things? Well, if FSC were 1.0, we could start with the speed of light. We've got a way of measuring that in meters and in seconds, and we can flip that back around and say, hey, the speed of light comes in to the calculation of the fine structure constant. And I actually use Bing's AI, their ChatGPT, to flip the math to come up with what would the value of C be if it's based on the fine structure constant. It works. It's a ratio. It's great. You can convert things. So once we have the speed of light and we know that those other constants are based upon the speed of light, we can now calculate the speed of light, the meter, and the second. And that's where the other things come into play. So we'd have a new basis, and it wouldn't change anything that we've already got. Much like we, have the kilogram is what the kilogram is, we'd now have a new basis for it. So it's not intolerable. We can get there from here. But until, the SI decides they're going to do something like this to try and come up with a physical basis that matches real world, it's not going to happen. It's just my harebrained scheme of, guys, if you're looking for a common basis that matches reality, that matches the physical world, that's truly a constant, here's the FSC. Back everything off the FSC, and I think you'll find that, you've got a better place to be. If not, then it's kind of like it is what it is. So we can say, if they made FSC 1.0, fine. If SI doesn't do it, it'll never happen. So that's 1.0. That's from where we start counting above 0. What about our unitary steps of 1, like 1, 2, 3, 4? Maybe the separation between them isn't supposed to be a constant. Maybe it's supposed to be, you've heard of this one before, the golden ratio or the Fibonacci sequence. If you're counting using the golden ratio, the numbers are 1, 2, 3, 5, 8, 13, 21. Because to get to the next number, you add the previous two numbers. So 1 plus 2 is 3, 2 plus 3 is 5, 5 plus 3 is 8, 8 plus 5 is 13. But I'll save that for some future presentation because that one's even more far-fetched, more harebrained, less likely. So now that I have the fine structure constant out of my brain and off my plate, what about that speed of light? What about that index of refraction of 1.0? I'm working on another presentation of decay of the Higgs boson and how that's how we get maybe the interstellar redshift. And if that were the case, maybe the speed of light could be faster if the index of refraction were less than 1.0. Okay. I know what it is. There was math. Math always puts people to sleep.
Some people.
But those who
My-
wake up early, it's tough to be awake at this time.
Yeah. And some people might call it science humor. I'm just poking fun at the SI, which I've been known to do. Any particular comments regarding tonight's presentation? Otherwise, other than don't ever do that again.
No, it was good.
Well, interesting.
I
It's,
was
It was
going to-
great.
it's
One at a time.
strangling my brains.
Anything else before we close for tonight?
No?
Hearing nothing. Thanks everyone for joining. And we'll
Thank
talk-
you. Good night.
Nice.
for the education.
Good night, everyone.
Wild
Bye.
See you later. Okay.